In our third video from chapter 6, we are going to get two new reactions. The first one is the hydroboration-oxidation, and then we'll finish the video with the addition of halogens to alkenes. So first up, hydroboration-oxidation, which you'll see me abbreviate as HBO as a shorthand notation. This is first the addition of borane to an alkene, but the net result of the hydroboration with the oxidation is the conversion of an alkene to an alcohol, okay, by two successive reactions. First the hydroboration, then the oxidation, okay, which is the second reaction from chapter 6 to take an alkene to an alcohol. The acid catalyzed addition of water does the same thing. Okay, but the products for the two will be different, as you'll see in just a second. Keep that in mind when you're keeping your list of reactions from chapter 6. Acid catalyzed addition of water and HBO both convert an alkene to an alcohol, yeah, but you get a different alcohol. So hang tight on that. We'll see it in just a second. Here's an example of a result we would get from propene here. The hydroboration occurs in step 1, the oxidation in step 2. Okay. This is the general reaction scheme. Okay. BH3 here is the electrophile, even though it isn't positively charged because it has a vacant p orbital, as we'll see in just a second. An alkene to an alcohol. This notation here, when you see a 1 and a 2 in the arrow, means it's a two-step reaction. It's not all done in the same reaction mixture. First you do step 1, then you do step 2. So this is the hydroboration in step 1, the oxidation in step 2. Okay. So why does borane act as an electrophile here? Right? Just like the methyl cation that we've seen before, BH3 has an incomplete octet. And if you go back and check the notes when we learned about electrophiles, that is one of the things, the criteria for finding an electrophile. That incomplete octet means we have an empty p orbital that can accept electrons. So that's what's acting as our electrophile here. The nucleophile, as we'll see in a second, ends up being hydride, one of those hydrogens that's bonded to boron. Now here's the difference that I was alluding to. Taking propene here, right, acid catalyzed addition of water, following Markovnikov's rule, you're going to get 2-propanol as your major product and your only product. And that is because we first add H plus to this carbon here, puts a carbocation and C2, and then we get water coming in as a nucleophile and then deprotonate the protonates alcohol. Okay, 3 steps overall, get 2-propanol. But notice with the hydroboration oxidation, 1-propanol is our only product. Okay. And the reason for that is we're still following Markovnikov's rule, but we have a different electrophile. Up here, H plus was the electrophile. Okay. Down here, as we just saw, boron, BH3, is acting as the electrophile. Okay. So the boron actually gets added to the same carbon as the hydrogen did before. But then when the first reaction is over, right, notice that we've got reaction 2 here. It's an aqueous solution of sodium hydroxide and hydrogen peroxide. Okay. That oxidation step causes OH here to take the place of boron, and that's how we get our alcohol as the product. Right. In the first step, as I just mentioned, hydride is a nucleophile. So like the water nucleophile ends up on C2, here a hydrogen nucleophile ended up on C2. Okay. So that'll hopefully make a little bit of sense now. It'll make more sense when we see the mechanism. Just keep in mind that the alcohols are flipped between an acid catalyzed addition of water and a hydroboration oxidation. As I've alluded to, we aren't breaking any of the rules. Okay? And this is why you want to learn the rules, not just memorize products. Because in both of those reactions, we are following the rules. Our electrophile is adding to the sp2 carbon that's bonded to the most hydrogens, Markovnikov's rule. If it's acid catalyzed addition of water, H plus is the electrophile, water is the nucleophile. I just mentioned that. In the HBO, borane is the electrophile, H minus is the nucleophile. So know the rule, identify the electrophile and the nucleophile, put them together in the right way. So let's look at an example. Showing our bond here in BH3, this is how our mechanism occurs. The empty p orbital in boron accepts the pi electrons from the alkene and forms a bond with one of the sp2 carbons, the one with more hydrogens. Right? It forms that sigma bond here. Simultaneously, this boron hydrogen bond breaks in the hydride when it's H minus, right? H with a pair of electrons, it's called hydride. That hydride gets transferred over to the other vinyl carbon as the nucleophile. So that's what's happening here. This is called a concerted reaction. Unlike the acid catalyzed addition of water, where we form the carbocation and then add the nucleophile. Here in the hydroboration step, notice this is just hydroboration, not oxidation. Everything happens at once. That's called a concerted reaction. That's a definition you should definitely know from chapter 6. Bond making and bond breaking all happens in the same time. Right? They're in concert with one another, like an orchestra. So it's a concerted reaction. Hydroboration is a concerted reaction. Why is this still following the same rule? Right? In our transition state, we get a delta positive on our carbon. Yep. And I want that delta positive to be in the more stable position. Yep. When I'm adding borane, the delta positive here, my electrophile adds to the carbon with more hydrogens, put the delta positive on the more substituted carbon, which is more stable. Same thing over here, which we already talked about for addition of a hydrogen halide. If you have a difference in concentrations, right? BH3 has 3 hydrogens. Okay. So in theory, you can form what's called a dialkyl borane and a trialkyl borane. You just continue after it reacted once, picked up an alkyl group, and then you can do it with one hydrogen or another hydrogen. Now, as you move to the dialkyl and trialkyl borane, okay, those bulkier substituents, as you add on the alkyl groups, have even more preference for going on the end, going to the carbon with more hydrogens, the less substituted sp2 vinyl carbon. So it's actually advantageous in terms of selectivity for your reaction to use bulkier substituents. And something that's used really commonly for the hydroboration part of an HBO is this guy right here, 9-bora-bicyclo-331-nonane, abbreviated as 9BBN. You should know that for chapter 6 for your test and moving forward. It's a common reagent that's used for hydroborations. Okay? Because of those two bulk, it's really just one group, but it's got 2 bonds going to boron. That giant group, it sterically hinders and makes it an even better reagent to use for hydroboration. Okay, so make sure you've got that jotted down, 9BBN. If you see that, you know you're doing a hydroboration. Yep. But in terms of writing out the mechanism, it's the same exact thing. We just changed this from 2 hydrogens to 2 alkyl groups. And you don't have to draw the whole structure of 9BBN, just know what it's used for and write it as HBr2. Piece of cake. It just has greater selectivity. But that's just the hydroboration. We also have the oxidation step, okay, to replace the borane with hydroxide and give us our final product as an alcohol. It's done again with an aqueous solution of hydroxide and hydrogen peroxide. It's considered an oxidation because we're increasing the number of carbon-oxygen bonds. Okay. Getting one more CO bond there. So what's the mechanism? Okay. Well, first I have my hydrogen peroxide ion come in. Right? It's been deprotonated in a basic solution. So my hydrogen peroxide comes in and attacks boron. Okay. Shares a pair of electrons there to give me this negatively charged boron, still acting as an electrophile. Here's our electrophile. Here's our nucleophile, negatively charged. Okay. Then I do what's called an alkyl shift. Okay, similar to a methyl shift that we saw with carbocation rearrangements. I have this alkyl shift over for the carbon-boron bond over to oxygen, okay, and it displaces this hydroxide ion. And so it's effectively just a bond moving over to carbon, popping off that OH. Okay. That makes boron neutral again and makes it more stable. Okay. Because that's got such a low electronegativity, it's unstable when it has a negative charge here. So it's more stable on the right-hand side there. Then that hydroxide ion comes back in, shares a pair of electrons with boron, and then it eliminates, right, comes in bonds, and then pops off, eliminates the alkoxide ion. Yep. That formation here of BOH is more stable, pops off the alkoxide ion. That's going to be, right, sufficiently basic to pick up a hydrogen off of water. And then I form my alcohol as a byproduct and alcohol as a product of the reaction here, and hydroxide as a byproduct. A couple of steps there. Really, it's just shifting bonds around, kicking stuff off, bringing it back in. The oxidation is the most challenging of the mechanisms I've introduced in this video. The key thing, know the reagents, know what's used. You can either use borane in THF. I didn't mention this before. THF is just a solvent, tetrahydrofuran, just a solvent in this case, not participating in the reaction. And then your aqueous solution of hydrogen peroxide and hydroxide for the oxidation. So know those for the HBO, and know that you can also use 9-BBN in the first step. What's nice about the hydroboration-oxidation is there's no carbocation rearrangement. You don't have to worry about that, okay? Addition of a hydrogen halide, acid catalyzed addition of water, you get a carbocation. You have to worry about carbocation rearrangement. Here, you don't. You just put the alcohol, the OH, right? If you're just asked to draw the product, put the OH on the carbon that had more hydrogens. All right, so that's the hydroboration-oxidation. The next reaction from this section, addition of halogens. Taking an alkene and adding, right, Cl2 or Br2. It does require an inert solvent, such as dichloromethane. That's DCM here. And the product of adding a halogen to an alkene is called a vicinal dihalogen. You add a halogen to two adjacent carbons, the two things that were previously involved in the double bond, now both get a halogen. Okay. Here with bromide, here with chloride. My keyword there, another vocab word from this section, vicinal. Two carbons next to one another. All right, so you see it with bromine, you see it with chlorine. This is dichloromethane, CH2Cl2. But the weird question, right? We know for everything in chapter 6, my alkene is a nucleophile. So how is this thing acting as an electrophile? Is the criteria for an electrophile, empty p orbital, partial positive charge, full positive charge. None of which we have for these at first glance, Br2 or Cl2. But both bromine and chlorine are polarizable. Okay? The bond between the two of them is actually easily broken because when the alkene approaches, it induces a dipole in the bond, which causes one of the halogens to have a partial positive and act as an electrophile. Right? Partial positive can be an electrophile. And that's what's going on right here. Okay, the alkene approaches, right, induces a charge, and then, right, when it induces the charge here, it can attack and act as the electrophile. Okay. It does require, though, an end-on approach. We've talked about kinetics in the past and orientation being significant. Yep, this does require, these guys can't line up side by side. It does require an end-on approach of the halogen. Yep. It induces a dipole here, partial positive on this bromine, partial negative over here. That allows the alkene to attack the bromine. Yep. This bond breaks. The shared electrons that were previously in the Br2 bond breaks and goes here to form bromide there. But bromine has a large enough electron cloud that it actually approaches this other carbon simultaneously. Right? It's a big cloud that sits right on top of both of these. So notice it forms two bonds temporarily in this intermediate. It's called a cyclic bromonium ion. Or if it was chlorine, it would be a cyclic chloronium ion, which again is super convenient because I'm not forming a carbocation. So I don't have to worry about carbocation rearrangement. But there is a lot of steric strain here, and I have a positive charge on something that's electronegative, so it's not super stable. Therefore, my bromide comes in, attacks this carbon, breaks that bond, and I form my vicinal dibromide. This is a very fast reaction. This is the slow step. This is the fast step. Rapid reaction with a nucleophile. If it were chlorine, the mechanism is the exact same. Right, just change the bromines to chlorines throughout. Same mechanism. I already mentioned no carbocation rearrangement, so that's super convenient. Okay, but notice we've only done this with bromine and chlorine. Alkenes don't add F2 and they don't add I2. Right, the reaction with fluorine F2 is explosive, and the reaction with I2 here, iodine, is thermodynamically unfavorable. Forming a vicinal diiodide here, these guys are too large and too close to one another sterically. So even if this is formed, notice the equilibrium arrow. It rapidly decomposes back to the alkene in I2. So that's nice. With this reaction, the addition of halogens, you only need Br2 or Cl2. Those are the only ones you have to worry about. Otherwise, it won't react. But do pay attention to the solvent. Dichloromethane is what we need for that reaction to go with Cl2 or Br2. If you have another solvent, it might interfere with your product. Okay? So you always have to look out for the conditions. If you have a halogen in an aqueous solution, right, you form what's known as a halohydrin. Bromohydrin if it's bromine, or chlorohydrin if it's chlorine. Right? So a halohydrin is a molecule that contains both a halogen and OH in alcohol. So let's think about how that happens, because notice it's the major product here. Right? Consider the mechanism. Well, the first two steps are the same. Sorry, first step and a half here. But here, now I have a water nucleophile. Right? Previously, bromide was my only nucleophile. But here I have a water nucleophile that can come in and attack this carbon and form, right, first a protonated halohydrin, and then after it gets deprotonated, the OH. Okay? So two possible nucleophiles. Sometimes this is going to attack, but in an aqueous solution, water is way more concentrated. Okay? So that's what's going to add to the carbon. More concentrated, higher concentration of the product. Okay? And again, it forms this protonated product, strong acid, sheds the hydrogen, sheds the proton. So now the question becomes, if I form a halohydrin, how do I know where to put the halogen and where do I put the water? Well, to pay attention to Markovnikov's rule, right? Still guides me the same way. Br or Cl is acting as the electrophile, so it goes to the carbon that had more hydrogens. Okay? CH2 versus CH here. This is the one that ends up with bromine, okay? Because bromine was the electrophile, because that gives me the partial positive on the more substituted carbon, and therefore the more stable transition state. So notice here, right? Carbon with more hydrogens, the one that ends up with bromine, the other one gets the OH. If you're forming a halohydrin. If you're forming a vicinal dihalide, right, it's the same thing on two adjacent carbons, so you don't have to worry about it. Other things you might look out for, okay? If you have an alcohol in there, you might form an ether. Okay? Same exact mechanism, just instead of water, now it's methanol. Okay? Over here, if you have another nucleophile in solution, that might interfere as well. Okay? My electrophile in the first step goes to the carbon, but then I might add a chlorine in the second step. The mechanism's always the same, but the concentrations and the conditions are important. The higher concentrations of added nucleophiles change the product by participating in the second step, right? What's going on right here, the attack of this nucleophile. So I recommend, this is our final slide 62 from this video, you practice these on your own. Draw the mechanisms out and see how you can make these products. Be able to do that for the hydroboration-oxidation, be able to do it for these halogens in a variety of conditions, either by themselves in an inert solvent or with other nucleophiles like we have here.